Hi, I'm Dr. Tom Calabrese, and welcome to this edition of Insights into Computer Science. In our previous video, we talked about the mechanics of building a linked list. While you may have found that confusing to some extent, believe me that with a little practice, you'll be a whiz at it in no time. This week, we want to examine some of the really great things we can do with these linked lists. Linked lists and arrays are considered the building blocks for all of the advanced data types such as queues, stacks, trees, graphs, and hash tables. Queues, for example, are linked lists that are governed by the FIFO, or first in, first out rule. Essentially, we need to create a special header with two pointers, one that points to the front of the queue and one that points to the rear of the queue, and also contains maybe some metadata like the count. Think of the queue as a line at the movies. The tickets are sold to the person at the front of the line, and new people get in the queue by entering the rear of the line. So it is with our queued linked list implementation. In our illustration, we start with a header with 3 nodes. If a 4th node is created via the malloc, we add it to the rear of the queue by setting the next field of node 3 to the new underscore pointer pointing to node 4, and then reassigning the header.r pointer, or the rear pointer, to that same new underscore pointer. This creates a new list that looks like this. We call this the enqueue process. To remove something from the queue, we simply go to the F pointer, which is pointing to the first node that we entered into the queue, and return the data of that node to the calling program. We also have to reset the F pointer, so the new value of the F pointer will be assigned the old value of the F pointer next field, meaning the new value of front pointer is assigned the old value of the front pointer's next field. So in our illustration, node 1's next pointer points to node 2. So after you have saved node 1's data, you update the pointer of the header to point to node 2. Then return node 1 data to the calling program, and you're done. Remember, it's always a good programming practice to free the memory of the node you just removed. Queues never allow things to be inserted or removed in the middle of the linked list, because if you could, then it would no longer be a queue. In other words, the FIFO rule is strictly enforced, and that creates the queue. Stacks work based on the FILO, or first in, last out rule. That means that to create a stack out of a linked list, we first create a header with a pointer to the stack top and a field for the count, or metadata. To add something to a stack, assign the stack top pointer to the next field of the newly created node. In other words, don't lose the original stack top. Then the stack top gets reassigned to new pointer, or the new node. To pop something, you simply return the data belonging to the node that stack top is currently pointing to, and then reset the stack top to point to the next field of the recently popped node. This preserves the chain. As you can see, this is really not all that complicated. Once you understand how to manipulate the pointers, it's usually a pretty smooth development cycle. I always tell my students to draw out the sequence and then simply code what you see. In other words, use the code as your pencil. My favorite of the advanced data structures has always been the hash table. When we consider search algorithms in future videos, you'll see that the time to search or sort a list of an array is relative to the size of that list. And thus, the bigger the list, the more careful you have to be in writing the code to search or sort it. For instance, a simple bubble sort is an n-squared sort time, meaning if we have to add something to a list with 10 things, it might mean that we have to do 100 operations to get it in the right spot for a worst case. If we have 100 items in a list, the worst case is that we might have to do 10,000 manipulations to get one thing into the right spot, and so on. This is really bad. Luckily, we can use a hash table to improve on this. A hash is a mathematical calculation that is based on the modulo operator, the percent sign in C, that allows for us to make a computation and then force it into a range by returning the integer remainder of a division. For example, if I use a modulo of 5, any number that I use will return something in the range of 0 through 4. So 11 mod 5 returns 1. 10 mod 5 returns 0. 12 mod 5 returns 2. 23 mod 5 returns 3, and so on. A hash table is an array of headers that point to a series of linked lists where we will store the data as it arrives. As an example, say that we want to make a hash table of students sorted by first name. To do this, we will revisit our old familiar node_t. You can see that the code is exactly the same as we used before. Now you can create a type def for the header that points to it. Why a type def? Because we're going to make a collection of type defs in our hash table. So to do that, you see the type def header structure has a node pointer to the front and the integer for the count for metadata, and we made it header_t since it's not actually a header but a map of the header. Remember that you have to do the type def for the node first because the header needs to create a node pointer to one of those, so it has to exist before you start it. Inside the main program, simply create the hash table using this code. First, we're going to create the hash value. That's where the modulo calculation will return its hash. The hash table size, because eventually you want to be able to adjust the size of a hash table. And then the hash table itself, which as you can see is an array of size ht_size of types header_t. So basically it's a table of pointers. Now we create a hash formula. This formula is read, the sum of all ASCII values of the letter in the name, add them together, and then mod 5. Remember, this will always return a number between 0 and 4. So let's try it. Add the name Tom. The ASCII value for this is 84 for the capital T, 111 for the small o, and 109 for the small m. This is a sum of 304. 304 divided by 5 returns a remainder of 4, and that will be used as our hash value, or HV. The hash value corresponds to the index of the array, and this is the location where we will try to store the Tom node. Now, in this case, when we look at hash_table 4, we see that it is a null, so the chain is empty and Tom can fit right in there. So using the code we developed in the last video, we can see that it is simple to add the Tom node to that chain. Now let's do the same thing for the name Pete, which yields a hash value of 3. Like the Tom node, the Pete node is the first element in the chain at hash table sub 3, so just add him in. Now let's try Mary. This hash value turns out to be 4. This means that when I go to add Mary, I will see that the Tom node is already there. And so I will insert the Mary node before the Tom node since they need to be alphabetical by first name, and we wind up with the updated chain of 2 nodes shown here. Now, if I search for, say, Tom, I simply recalculate the hash, go to the index in the array, and I will find Tom as the second element. If, however, I search, say, Jill, I will find that when I search for that, her HV is 0, and the chain is null when I go to that place in the array, and so therefore Jill is not in the list. Now, if you're paying attention, what this means is that I'm adding and searching for things in near constant time. And things just don't get any better than that. If, however, too many things hash to the same HV, then the performance will deteriorate to the order of big O of n, or n things. So the size of the list, I'll have to search each thing. Now, that's still better than n squared by a lot, but is far worse than constant time. This is known as the load. The greater the load on any one of the lists, the worse the performance will be. To counteract this effect, we need to periodically rehash by enlarging the hash table. Thus, by increasing the size of the table, the hope is that the data will spread more evenly and the list will return to being a manageable length. Thus, the performance will return to expected levels. Hash tables are really important and are often used as the data structure of choice in routing tables in network designs. Now, if you are enrolled in this course, you'll see that this week's assignment is to create such a hash table as the one we've been working on. So I'll leave the remaining details to you for homework. If you're not in the course, try and build one and compare its performance to other data structures, and you will see just how powerful this is. So until next time,